Section 6.2, Day 1, Transforming and Combining Random Variables. After this section, you should be able to describe the effects of performing linear transformations on random variables. In Section 6.1, we learned the mean and the standard deviation give us important information about a random variable. In this section, we'll learn how the mean and the standard deviation are affected by transformations on random variables. If you remember back in Chapter 2 when we were dealing with normal distributions and density curves, we studied the effects of linear transformations on shape, center, and spread of a distribution of data. Recall, when you add or subtract a constant to each observation, your measures of center, mean, and median, and also location, are changed by adding that value to those. It does not change the shape or the measure of spread when you add a constant to each observation. 2. When you're multiplying or dividing each observation by a constant, B is going to multiply or divide the measure of center and location by B. It's going to multiply your measure of spread by the absolute value of B, and it will not change the shape of your distribution. Let's take a look at how these transformations relate to a discrete random variable. Here's an example. Pete's Jeep Tours offer a popular half-day trip of a tourist area. There must be at least 2 passengers for the trip to run, and the vehicle will hold up to 6 passengers. I'm going to define X as the number of passengers on a randomly selected day. So you can see the possible outcomes for a number of passengers would be 2, 3, 4, 5, and 6. And you can see the probabilities of these outcomes listed below. Here's a picture of the distribution. If I were to calculate the mean, it ends up being 3.75. Remember, the formula for mean is taking each individual observation times its probability and adding those all together. And the standard deviation ends up being 1.09. The formula for that is taking each individual outcome minus mu sub x, or the mean that we calculated, squaring it, multiplying it by the probability, and then adding those all together. Again, this means on average you would be off from 3.75 by 1.09 passengers on a randomly selected day. Here's a transformation. Let's say Pete charges $150 per passenger. The random variable now C, I'm renaming it, describes the amount Pete collects on a randomly selected day. So take each of my individual outcomes and multiply them by 150. I'd end up with my outcomes of being 300, 450, 600, 750, and 900. Here's a picture of that distribution. If I were to calculate the mean of this probability distribution, it would end up being 562.5, and the standard deviation would be 163.5. If I compare the shape, center, and spread of the two distributions, notice the shape is the same. The center on the first was 3.75, and the center of the second, which is the amount Pete collects, is 562.5. And if I compare the spread, the standard deviation for the first, which is number of passengers, is 1.09, and the second, which is for how much Pete collects, is 163.5. What do you notice about these? Hopefully you noticed how multiplying or dividing a constant affects a random variable. When you multiply or divide each value of a random variable by a number b, it multiplies or divides the measure of the center and location, meaning the mean, the median, quartiles, and percentiles, by that value b, and it multiplies or divides the measure of spread, meaning your range, interquartile range, or standard deviation, by the absolute value of b. The shape of the distribution was identical for both pictures, so that does not change. Multiplying a random variable by a constant b will multiply the variance by b squared. Keep in mind the variance is nothing more than the standard deviation squared. Now let's take a look at this again. Consider Pete's Jeep's tour again, and we've got our random variable c defined as the amount Pete collects. Let's suppose it costs Pete $100 per trip to buy permits, gas, and a ferry pass. The random variable v describes the profit that Pete would make on a randomly selected day. So you can see that all my individual outcomes from the collected, I have subtracted 100 from each of those. If I were then to calculate the mean and the standard deviation using the formulas we covered back in section 6.1, I would end up with having a mean of 462.5 and a standard deviation of 163.5. In comparing the shape, the center, and the spread of the two probability distributions, meaning the cost and the profit, the shape ends up being the same. The center is decreased by 100 from 562.5 down to 462.5. And the standard deviation, which is the measure of spread, has stayed the same at 163.5. So how does adding or subtracting a constant affect a random variable? Adding the same number a, which could be positive or negative, to each value of a random variable adds a to the measure of center and location, and it does not change the measure of spread at all, and the shape will not change. Whether we are dealing with data or random variables, the effects of linear transformations are the same, just like they were back in chapter 2. If y is equal to a plus bx, meaning y is a random variable and x is a random variable now that we're multiplying by b and adding a to it to get the random variable y, and it's a linear transformation, then the probability distribution of y will have the exact same shape as the probability distribution of x. Mu sub y, the mean of y, will then equal a plus b times the mean of x, and the standard deviation of y will equal the absolute value of the standard deviation of x. Again, standard deviation cannot be negative, so you need to multiply by the absolute value of b. This is the end of the notes on the linear transformations. In the next lesson, we will talk about combining two just random variables.